So what is a transformer? Transformers operate on a concept called sequence-to-sequence learning. Essentially, they take a sequence of tokens as an input and predict the next token in the output. A great example of this is language translation. Imagine inputting "Good morning" in English, and the transformer processes this and outputs the translation in languages like Japanese, Korean, or German. The key is how it efficiently processes the relationship between words. Since we know what a transformer is, let's dig a bit deep about them. A transformer has two primary components, encoder and decoder. Encoder identifies relationship between parts of the input sequence, whereas the decoder uses these relationships to generate the output sequence. This division is what allows transformers to handle tasks like text translation or summarizations with remarkable accuracy. Now that we have the idea of transformers, let's discuss how they evolved. Before transformers, there were other neural networks like RNN, recurrent neural networks, invented by David Rumelhart in 1986. However, RNNs faced significant challenges. They would forget early parts of the sequence as they processed longer ones and couldn't handle dependencies efficiently. Additionally, RNN relied on recurrence, which made them inefficient and incapable of parallelization. Then came long short-term memory, introduced by Howiter and Schmidhuber in 1997. Long short-term memory improved by remembering sequences for a longer duration and addressing some of the memory issues in RNNs. However, they were slow to train and difficult to manage at scale. Finally, transformers transformed neural networks. First introduced in the landmark paper, "Attention is All You Need." Transformers addressed all the problems faced by RNNs and LSTMs. They used a completely attention-based mechanism, eliminating reliance on recurrence. This made transformers capable of remembering context efficiently, training faster, and being parallelized, enabling multitasking and significantly speeding up processes. Now let's discuss on the attention mechanism. Think about this sentence: "This cat wants to jump on the box." The attention mechanism identifies the most relevant parts of this sentence, like cat, jump, and box, and focuses on these elements while processing the data. Now that we know how transformers have evolved, now let's discuss their architecture. A transformer consists of two main components, an encoder and a decoder, each typically consisting 6 layers. Inside the encoder, there is one attention layer and one feed-forward layer, while the decoder contains 2 attention layers and one feed-forward layer. The magic of parallelism comes from how data is fed into the network. In the attention layer, all the words are processed simultaneously, with each word forming combinations with other in the sentence. This allows the model to capture relationships and context efficiently. After processing in the attention layer, the data is sent to the feed-forward layer, where it is learned layer by layer. The input to the encoder and decoder are the raw input embeddings, which are numerical representation of words. On top of these embeddings, positional encodings are added to help the model understand the position and the order of each word in the sequence. If we simplify embeddings, there are essentially vector representation of words in an n-dimensional space. At the top of the architecture, there are 2 layers of the output probabilities, converting the final output into the form of human can understand. These inputs are represented as vectors with their length corresponding to the size of vocabulary. Now, what truly makes transformer unique is the inclusion of normalization layers, which normalize the output from sub-layers. Additionally, skip connections, the dark arrows in the architecture, forward critical information that bypasses self-attention or fed-forward layers directly to the normalization layers. This ensures the model does not forget important details and effectively passes vital information further into the network. Now, moving forward, let's discuss why transformers are important. Transformers are vital because they utilize semi-supervised learning. They are trained on massive unlabeled datasets, enabling them to generalize across a wide range of tasks. Unlike older models, transformers don't need to process data sequentially. Their attention mechanism allows them to focus on the most relevant context, which significantly speeds up training. Transformers revolutionize data processing by eliminating the need to handle data sequentially. allowing for parallel processing and significantly enhancing efficiency. The attention mechanism lies at the core of transformers, enabling the model to focus on the most relevant parts of the input sequence and improving accuracy and understanding of context. Furthermore, transformers excel at providing context, ensuring that the meaning of each word or token is accurately interpreted within its surroundings. Lastly, these models dramatically speeds up the training process, making them faster and more efficient compared to traditional neural networks, thus redefining AI's capabilities across diverse applications. Now that we know why transformers are important, let's discuss some applications. We have OpenAI's GPT, a groundbreaking model that leverages the power of transformers for natural language processing tasks. Additionally, Google has developed several transformer-based models including Vision Transformer for image recognition, BERT, bidirectional encoder representations from transformers for understanding the context of words in a sentence, and T5, which stands for Text-to-Text Transfer Transformer for a wide range of text generation tasks. Microsoft has also contributed with DBERT, decoding enhanced BERT with disentangled attention, a model designed to improve contextually understanding and enhance NLP applications. These models demonstrate the versatility and impact of transformer architecture across various domains. Now that we know the application of transformers, how about checking their real-time products? Transformers have become an integral part of many real-world products that we use daily. Examples include Grammarly, which leverages transformers for advanced grammar and writing assistance. Google Search and its translation tools powered by models like BERT and T5, and ChatGPT, OpenAI's conversational AI that relies on the generative pre-trained transformer architecture. Additionally, Meta's deepfake detector uses transformer-based models for facial recognition tasks. These applications highlight how transformers have revolutionized technology, seamlessly integrating it into tools that enhance our everyday lives. In conclusion, transformers are changing the tech world by enabling smarter, faster, and more efficient AI systems. Whether it's generating text, translating languages, or enhancing search engines, these models are the cornerstone of modern